In this video, we are going to look at phase transition. Please read the OER textbook chapter section 10.3. In this section, we are going to focus our attention on the heat that involved with the process of phase transition. Earlier on page 56, we learned about the change between states, right? We learned about the relationship between kinetic energy and intermolecular forces that hold each of those molecules together. So in this chapter section, we're actually going to focus our attention on the heat that involved with each of those phase transition. So first, let's take a look at when solid change to liquid. Okay, so this process is called fusion or melting. And when liquid change to gas would be vaporization. The enthalpy change that involved with this process would be the endothermic process because require heat to overcome the IMF that hold molecule tied together in the previous state, right? So in this case, you will see that there is a certain amount that involved with each of these process, okay? Again, so notice that the subscript fields, right, refer to the fusion process and VAP is referred to vaporization process, okay? And when the phase transition occur when solid going to gas directly, that process is called sublimation, and the enthalpy change that involved with this would be the enthalpy change of sublimation. All of these are going to be reported in kilojoule per mole, okay, so per mole of the substance, okay. All right, so the opposite process, right, the reverse process of this condensation and freezing is going to involve with the heat as well. But in this case, the heat is going to have to be released. Okay, so it's going to involve with the exothermic process. The quantity of the heat involved with condensation and freezing is going to be the same quantity as the heat of vaporization and fusion, but the sign would be the opposite because the sign would tell you how the heat is leaving the system, right? So in this case, the amount would be the same. The only thing different is the sign. Okay, so same thing here. Okay, so that means in this case, the heat involved with freezing would be a negative of the enthalpy of fusion. So the last one is the position is going to be the same thing as well as the amount would be the same as sublimation, but the sign would be the opposite. Next thing, we are going to focus our attention on each of these processes and factors that affect them. Okay, so let's take a look at first vaporization and condensation. So again, when I talk about vaporization or condensation, you just know that they are just the opposite process, okay? So in this case, if you're looking at how intermolecular forces affect vaporization, you can looking at two different things, right? If you have two substances, one has a weak intermolecular forces that hold them together, and the other one have strong intermolecular forces that hold them together strongly, you are going to be able to differentiate them in two categories. The one that have weak IMF, they are going to be able to change the state from liquid to gas very easily, right? Because it doesn't require much of the energy to overcome the IMF. So these are going to be the one that is referred as volatile substances. Okay, so for those that have a strong IMF, they are going to not change state from liquid to gas easily. So those are what we refer to as non-volatile substances. The surface area also has an effect on vaporization as well. When you have liquid in a smaller surface area versus a larger surface area, you will observe that the one in a larger surface area will vaporize faster. So in this case, you will see that the amount of liquid in a vessel will disappear in a faster rate than in a smaller surface area. The temperature also has an effect on vaporization as well. If you have liquid at a high temperature, it's going to vaporize faster than at a low temperature. So the speed of vaporization depends on the temperature. Okay, so in this case, as the temperature increase, you are increasing the thermal energy to the molecule, right? So the molecule will move faster there, and also it's going to be able to overcome the IMF as well. So therefore, in this case, it's going to vaporize faster than at low temperature. Okay, so because when we talk about vaporization, we're looking at the change of the state between liquid to gas. So because we are forming gas and gas has pressure property, therefore in this case, we are going to take a look at the pressure of the vapor that is being produced during the vaporization process as well. Okay, so in this case, let's take a look at sample of water here, okay, in a flask, in a Erlenmeyer flask, and you are going to use the rubber stopper to close this so that way we have a closed system here. Okay, so eventually water would start to vaporize, right? So it's going to change from liquid to gas, okay? And if you let it sit long enough, the gases water molecule will also start to condense as well. Okay, so some of them will start to vaporize and some of them will start to condense. And that will be the point where the speed of the vaporization and the speed of condensation become equal. At this point, we refer this point as dynamic equilibrium. It's already at equilibrium, but it's dynamic, right? So it still happens, it's not static. Okay, so this when water, again, when water vaporizes equal to water condense. Okay, so at the pressure at this above this liquid, this is what we refer as vapor pressure. Okay, so again, vapor pressure is referred as the gas, right? So the gas above liquid, right? The pressure of the gas above liquid is what we refer as vapor pressure. So now we know what is vapor pressure. So the next thing we're going to take a look at is how the IMF affect the vapor pressure. Okay, so because IMF affect the vaporization, therefore it's going to have an effect on vapor pressure as well, right? So the one that has a weak IMF is going to vaporize faster, right, or easier than the one that have strong IMF. Therefore, in this case, the volatile substance is going to have higher vapor pressure always than the non-volatile substance, because again, because the amount of gas that produced above liquid would be more, right, in volatile substance than the non-volatile substances. Next, we're going to take a look at how surface area has an effect on vapor pressure. Okay, so in this case, we're going to look at two different surface area again. Okay, in this case, we are going to actually close those with rubber stoppers, so that way this one would be in a closed system. Okay, so that way they can reach the dynamic equilibrium. Okay, so if you do this, you will see that if you are comparing the same substance, you will see that the surface area will not have an effect on the vapor pressure at all, because the rate of vaporization is going to equal to the rate of condensation no matter what, right? So we can conclude that the surface area doesn't affect vapor pressure of the same liquid. Next, we're going to take a look at how temperature affect vapor pressure. Okay, so if you compare between two different temperature, you are going to observe that at high temperature, the water would be able to vaporize faster than is able to condense. Therefore, in this case, it's going to be able to generate more of the vapor, right, above the liquid, causing the vapor pressure to increase. So we can conclude that at high temperature, vapor pressure would be higher than at low temperature. Now let's take a look at example one. Okay, so example one is going to be similar to the previous lecture video that we learned. Okay, so we are going to take a look at this molecular structure. We are going to predict their polarity, and we are going to determine the type of IMF, because the strength of the IMF would determine how molecules interact between each other, right? So, and that is going to also affect how they are going to change physical state as well. Okay, so in this case, if you're looking at molecule A, B, C, and D, you will see that A contain the bond, carbon-carbon bond, and hydrogen-carbon bond. Those are non-polar bonds, making this molecule to be a non-polar molecule. So because A is non-polar molecule, the only type of IMF would present in A would be dispersion only. So now if I take a look at B, right? So B is going, now if you look at B, okay, so B contain this carbon, oxygen, and oxygen, hydrogen. Okay, so this bond right here is a polar bond, and you will see that they are not going to pull equally, right, within the whole molecule. It's going to cause asymmetric, like of the dipole moment. So therefore, in this case, this molecule would consider to be a polar molecule. Okay, because this molecule is polar molecule, is going to contain dispersion force and also dipole-dipole. But the strongest one would be the hydrogen bonding, because if you're looking at this, right, hydrogen is bonded directly to the oxygen. So that is the definition of the hydrogen bonding. Right? So that means in this case, molecule B exhibit hydrogen bonding. So now if you're looking at C, okay, so C, we have the CO bond right here. So these two are polar bonds, okay? And they are not actually pulling equally, because the actual geometry of this is not a linear like this. It's actually tetrahedral. So it's going to look like this, right, for an actual molecule. Okay, so because it's tetrahedral, the correct geometry is actually tetrahedral. So in this case, you will see that according to the tetrahedral geometry, you will see that the the dipole will not pull equally in all directions. Therefore, in this case, it's going to cause it to have a net dipole, causing this molecule C to be a polar molecule. Okay, because it's polar molecule, so it's going to exhibit dispersion, and also it's going to exhibit dipole as well. But this molecule will not have hydrogen bonding because hydrogen is not bonded directly to the oxygen. Okay, so it's just going to be dipole. Okay. Last one is only CC bond and hydrogen bond. So all of these bonds are nonpolar, therefore this molecule would be nonpolar. So it's going to be only dispersion that exhibits in this molecule. Okay. Now you know the type of IMF. The next thing you are going to look at is you are going to compare the strength of the IMF, right? So we know for sure hydrogen bonding is strongest. So this is going to be strongest, and dipole is going to be the second strongest. Now between dispersion, right? When they have the same type of IMF, the next thing you are going to take a look at is molar mass, right? If the molar mass are the same, then the last one we're going to take a look at is the molecular structure, right? Whether they are going to allow for a large surface area of interaction or a smaller surface area of interaction, right? So in this case, if you're looking at molar mass, clearly one is smaller than the other, so we can just use molar mass. So in this case, because the molecule A has the lowest molar mass, so therefore in this case, molecule A would have the weakest IMF, right? So compare between A and D, right? So because this is just dispersion, so A would have lower molar mass than B, therefore A would have the weakest IMF. Okay, so C would be stronger than D. Okay, so D would be actually slightly stronger than A, but A would be the weakest. Okay, so now since we know the relative strength of the IMF, the next thing we need to think about is how the IMF affect the state of matter, right? So think about this: if something is hold together strongly, right? So they don't want to change the state, right? So if it's going to change state, it's going to require more energy than the one that hold together weakly. So in this case, whatever that hold with each other strongly, it doesn't want to change state from liquid to gas. Remember, we're looking at the vapor pressure. Vapor pressure is the pressure of a gas above liquid, right? So in this case, the strongest one, which is contain the hydrogen bonding, would not want to convert from liquid to gas. Therefore, it's going to cause the vapor pressure above liquid to be low, right? So these are what we consider to be a non-volatile substances. Okay. So the one that have a weak IMF is going to be able to convert from liquid to gas very easily, causing more molecule of the gas phase, resulting in higher vapor pressure, right? Because the more molecule of gas, the pressure would also increase as well, according to what we learned in chapter 9. So in this case, if you want to rank the vapor pressure at constant temperature, you are going to get A to have the highest vapor pressure because it have the weakest IMF, right? So followed by D, and followed by C, and B would be the lowest. Okay, so in this case, we can say that A would consider to be like a volatile substance, and B would be non-volatile substance. All right, so the next one, we are going to take a look at the difference between the evaporation and boiling. Both of them are fall into the umbrella of vaporization. Okay, so when we talk about vaporization, it's actually, it refers to either evaporation or boiling. But what are the difference between these two? Okay, so we're going to take a look at one at a time. The difference between these two comes from the difference between their vapor pressure and the atmospheric pressure. Okay, so let's take a look at evaporation. When we talk about evaporation, it means that the vapor pressure above liquid is going to be less than the atmospheric pressure. So this is going to occur only at the surface. But when we talk about boiling, this is when the vapor pressure of the gas above liquid is actually equal to the atmospheric pressure. So that means the boiling is actually going to depend on atmospheric pressure. Okay, so when it's going to occur throughout liquid. Okay, so you are going to see the gas form like inside the liquid as well. Okay, so for example, as you see here, right, when it's boiling, right, so when the molecule has enough thermal energy to overcome the IMF, is going to change state from liquid to gas, and that gas molecule is going to move around, forming bubbles inside the liquid. Okay, so this is going to again occur throughout the liquid for boiling. So the boiling point is going to be the temperature at which vapor pressure equal to the external pressure or the atmospheric pressure. Now let's take a look at a graph plot between temperature and heat added. So if you have water at 20 degrees Celsius and if you keep adding heat to it, okay, so the water temperature will rise up until when it's reached to a certain temperature. So in this case, at 100 degrees Celsius. Okay, so you are going to start to see that when you are adding heat, the temperature is no longer changed. Okay, so at this point right here, we say that the temperature is constant. Okay, so this constant temperature tell us that this water is changing from liquid to gas. Okay, so at this point right here, temperature at this point is what we refer as boiling point. Okay, note that when liquid boils, temperature doesn't change, right? That's why the temperature constant. I would like you to highlight this. This is very important. Okay, so when liquid boils, temperature doesn't change at all. Now, when we talk about normal boiling point, we are looking at the temperature at which vapor pressure actually equal to the external pressure at the sea level. Okay, so in this case, because we define that sea level has the atmospheric pressure of 1 atm, so that means in this case we can say that normal boiling point is a temperature at which vapor pressure is actually equal to 1 atm. Okay, so in this case, anything else that is not at 1 atm, we are just going to call as boiling point. But the word normal boiling point, we are going to refer as at sea level or at 1 atm. Okay, so as you will see, right, so when substance boiling is depend on the external pressure or atmospheric pressure, so therefore in this case it depend on the altitude as well. As the altitude increase, the atmospheric pressure will also decrease as well because the gas is less dense at higher altitude, right? So that is going to cause the boiling point to also decrease as well, right? So as you see in these two pictures. All right, so what happened to boiling point of a substance when the external pressure is decreased? So as you see in the previous slide, right? So as the external pressure decreases, the boiling point also decreases as well. All right, so now we are going to take a look at the heat that involved with the vaporization now. So the heat that involved with changing the state of liquid to gas of 1 mole of substance, we refer this as the enthalpy change of the vaporization. Okay, so for water, it's 44 kilojoule per mole. Okay, now if you're looking at condensation, is the reverse process. So the delta H of the condensation would equal to the negative value of the delta H of vaporization, right? Because it's the reverse process. Here is the sample of common substance and their boiling point. Okay, so you probably noticed that if you're looking at the normal boiling point, you will see that the one that have stronger IMF, which are water and rubbing alcohol, those have hydrogen bonding, they are going to have higher boiling point, right? Because they are going to hold with each other strongly. So they are going to require more energy to overcome the IMF, right? So therefore their boiling point would increase. Okay, so now if you're looking at the heat of vaporization at boiling point, you will see that again, the stronger IMF is going to have a higher value of the vaporization, heat of vaporization as well, right? Because it's going to require more energy to overcome those IMF. Okay, so the last one, if you're looking at the heat of vaporization at temperature that is not boiling point, you will see that at this temperature, because this is at low temperature, so in order to change from liquid to gas, right, it's going to require more energy than the one that is already at the boiling point. Now, the calculation that involved with this is going to be similar to this example one. Okay, so it's going to give you amount of the substance, and it's going to ask you how much energy that requires to evaporate that certain amount of substance. Okay, so in this case, what you are going to do is, because you are given grams, right, but the heat of vaporization is involved with mole. So in this case, first step would be probably going from mass to mole first by using molar mass, and then convert from mole to kilojoule using this amount of delta H vaporization rate, because delta H has 2 units, right? So allow us to going from mole to kilojoule. Okay, so to solve this, again, you are going to convert from grams to mole using molar mass, right? And then going from mole to kilojoule using what is given here as the heat of vaporization. So the answer come out to be 18.1 kilojoule. So that means if you have 48.7 grams of dichloromethane, is going to require 18.1 kilojoule to convert from liquid to gas. Okay, so that's what it means. All right, so let's take a look at example 2. Okay, so I would like you to pause the video now and then resume the video again when you finish. Okay, so in this one, it's actually giving you heat. It's asking you to find mass. So same thing, right? So it's giving you heat. So therefore, you are going to need to convert to mole first, because the heat given right here is going to relate it to mole through this heat of vaporization. So in this case, after you get mole, then you're gonna be able to find out mass, right? So it's the reverse process from the example 1. Okay. So to solve this, set up 155 kilojoule. And because we know that every 40.7 kilojoule is going to involve 1 mole of water, and we know that every 1 mole of water is equal to 18.015 grams, right? This is the molar mass of water. Okay, so after you convert that, you are going to get 68.6 grams of water. Okay, so which means that if you have 68.6 grams of water, it's going to require 155 kilojoule from liquid water to water vapor. To summarize this, you will see that the type of calculation that you are going to see that involved with this type of calculation would be conversion from kilojoule to mole, right? And then mole to mass. And because we learned the conversion of mass before, right? So mass in here, you can also convert to different units as well. For example, like pounds, right? Kilograms, milligrams, micrograms, and things like that, right? And you also can use this mass to find out volume as well if you are given density, right? So this is go back into like Chem 121, right? So with those conversion, and same thing for kilojoule as well, right? So I might ask in joule, right? Different units, right? Or calories, right? Or kilocalorie or big cal, right? So you should be able to do that as well. Okay, so those are the type of conversion that you will see. All right, so the next thing we're gonna take a look at is the process of fusion and freezing. Okay, so melting point or fusion point. Okay, so melting point is referred to the temperature at which solid become liquid. Okay, so if you plot graph between temperature and heat again, right? So if you have a substance at -10 and you keep adding heat, the temperature of the substance will rise to a certain point. Okay, so this certain point right here, the substance would start to change state from liquid to solid. At this point, this temperature this is what we refer as melting point. Okay, melting point, if you're looking at the temperature, is going to have a constant temperature at melting point. Okay, so again, note this. I want you to jot this down. Okay, when solid melts, okay, temperature doesn't change at all. The temperature constant as you see the graph. And the heat that involved in this process we refer as enthalpy of fusion. Okay, so enthalpy of fusion is going to be the amount of heat required changing from solid to liquid by per 1 mole of the substance. So the reverse process, which is freezing, is going to have the same amount of heat that involved with the heat of fusion, except the side would be the opposite, right? Because one is endothermic, the opposite would be exothermic. All right, so now I would like to compare the amount of the heat of vaporization and the heat of fusion. You probably notice that the heat of fusion for each of these substances are a lot less than the heat of vaporization, right? The heat of vaporization are significantly higher than the heat of fusion. Why is that? Okay, so the reason for that is because when you are changing state from solid to liquid, okay, it's going to require less energy than changing the state from liquid to gas, because the solid and liquid are in a closer state than liquid and gas, right? Because like solid and liquid still have the internal forces hold them together, right? These two are considered to be a denser state than gas, right? So according to ideal gas law, right, gas do not interact at all. So that means in this case, if you are going to change the substance from liquid to gas, you need to destroy those IMF, right, in order for the substance convert to gas. So therefore, in this case, the reason why the delta H vaporization is significantly higher than the delta H of the fusion, because the delta H of fusion has a closer state between solid and liquid. All right, let's take a look at last two processes. Okay, so when we're looking at the state changing from solid to gas, we refer that as sublimation. The heat that required to change 1 mole of solid to gas, we are going to refer as enthalpy change sublimation. Okay, so For enthalpy of deposition would be the opposite, right, of the sublimation, but the opposite would be the different side. Okay, so the amount would be the same. Okay, but the sign would be the opposite. When we're looking at enthalpies, we know that enthalpies are state function, which mean they do not depend on the path taken. They depend on only initial and final state. So in this case, we can use that state function idea and also Hess's law to help us determine the enthalpy change of sublimation as well, if you know fusion and vaporization. Okay, so what do I mean by that? For example, right? So if you know the amount of enthalpy change of fusion, and if you know the amount of enthalpy change of vaporization, if you add these two together, it is going to equal to enthalpy change of sublimation, right? Because the it's only care about final and initial state. Okay, so that's what this refer to. So this graph right here is going to be based off state function idea and also Hess's law that we learned in previous lecture. The next thing we are going to take a look at is we are going to combine all those processes that we see earlier and put those ideas into water. We're going to look at when we heat water, what would happen. Okay, so this graph that you are going to about to see is called heating curve. Okay, so the opposite would be cooling curve, right? So let's take a look at this. If you have ice at 30 degrees Celsius, okay, and if you add heat, okay, so if you add heat to ice, of course, the temperature of ice would increase, right? The amount of heat that involved with this process can be calculated using Q equal MCAT, which is the same as what we learned in chapter 8, right? So you are going to use mass of ice multiplied by specific heat of ice and then change in temperature 0 and negative 30, right? So that would be delta T. Okay, so that is going to refer to the heat that involved with that process. Now, when temperature of ice increase to 0 degrees Celsius, you are going to see ice start to melt, right? So it's changing from solid to liquid, right? So at this point, you are going to notice that the temperature will not change at all, right? So similar to what we see earlier. Okay, so whenever the temperature constant, we know that those are the phase transition. Okay, so we're changing the state. So in this case, we know that at this point right here, when the temperature no longer change, this point, the temperature at this point we refer as melting point. Okay, so because the temperature doesn't change, we are not going to be able to use Q equal MCAT anymore. Remember, MCAT is involved with the change of temperature. So in this case, we can't do that because temperature doesn't change. So in this case, what you are going to do is we are going to use the heat of fusion instead in order to find out the heat that involved with this process. Because the heat is going to depend on the amount of the substance. Therefore, in this case, you are going to multiply the heat of fusion by the mole, right? The number of mole of substance that we are looking at. So the next thing, okay, so what happened is as ice melt, as it changed from solid to liquid, okay, so that after all ice melts, right, so it's all become liquid, then that liquid, as you add heat further, that liquid is going to increase the temperature. We are calling this process liquid warming, right? Liquid water is warming. So, and you will see that it's going to keep going up, right? So this one, again, you are changing the temperature, right? So it's changing from 0 to 100 degrees Celsius. Therefore, you can calculate for the heat involved with this as well by using Q equal MCAT. Okay, the difference is that you are going to use specific heat of water instead of ice in this case. Okay, so those two are not the same, and then the temperature change would be different. And when you heat it at 200 degrees Celsius, so again, so if I'm talking about the atmospheric pressure of 1 atm, so at 1 atm, you will see that as you heat water from 0 to 100 degrees Celsius, at 100 degrees Celsius, this point right here is when water start to change form to gas, right? So this point right here, you are going to observe constant temperature, right? Temperature doesn't change at all. The more you add heat, temperature doesn't change. At this point, when temperature doesn't change, you are actually going to observe the liquid water change state to gas. Okay, so this temperature right here is what we refer as boiling point. And if it's at 1 atm, okay, so this is referred as normal boiling point. So again, because this process, like segment 4, doesn't involve with temperature change, therefore we are not going to be able to use MCAT. Okay, so what we can use is we are going to use the amount of heat is going to involve with the heat of vaporization, right? Because vaporization is changing from liquid to gas. Okay, so again, it depends on the amount as well. So you need to multiply the number of mole of the substance to the heat of vaporization. So now if you look at this, right? So once liquid water change to gas completely, those gas, if you add heat further, is going to increase, right? So that means in this case, you actually heating vapor now. So the temperature of vapor would start to increase. Okay, so the amount of heat involved with this process of heating vapor is going to be Q equal MCAT that you can use. Okay, so one thing I want you to actually fix for me is the specific heat of the steam. Okay, so it's actually going to be 1.84. Okay, so can you fix that for me? All right, so that means if you're looking at water boil, right, the temperature of water is boiling and the temperature of the steam, you will see that steam is actually hotter than the boiling water. So I'm going to utilize all of this concept right here and help us to calculate the amount of heat that involved. Okay, so let's take a look at example one. So example one, we are going to take a look at how much heat is required to like convert ice, right, 9 grams of ice to water at 85 degrees Celsius. Okay, so I'm going to walk you through similar to the heating curve that we actually looked at before. Okay, so I'm going to take a look at what is given. Okay, so all of these are given. Okay, so we're gonna find heat. The plan is we have ice at negative 10 degrees Celsius. Okay, so when you are applying heat, okay, so ice will not change to liquid water right away. This temperature of ice need to heat up. Okay, so it's going to heat up to ice at 0 degrees Celsius. Ice at 0 degrees Celsius, then it's going to melt. Okay, so it's going to melt and become water. Okay, so water after ice melt is also going to be at 0 degrees Celsius as well. Remember, when it's changed state, the temperature will not change. Therefore, the temperature of ice here and water here will have to be the same, right? Because the temperature constant when during the phase transition. So now when you heat it further, that water at 0 degrees Celsius would have higher temperature, right? So it's going to have a higher temperature to 85 because we are looking at 85 degrees Celsius for this example. Okay, so that means if you're looking at this, right? So how do I calculate for heat? So in order to break this down, you are going to calculate heat for this one. Okay, you're going to calculate heat for this one, and you're going to calculate heat for this one. So that would be 3 calculations that you will need to do. If you're looking at the first process, right, you will notice that the temperature change. So this is whenever you see temperature change, you can use Q equal MCAT. Okay, so that means in this case, you can use Q equal MCAT. Just make sure that you use the correct specific heat. Okay, so this is of ice. Second one, the temperature doesn't change at all, so we cannot use Q equal MCAT. So in this case, you are going to use the heat of fusion instead. Okay, and the last one, because the temperature changed, so we are going to use Q equal MCAT. But the specific heat of water would be different from the specific heat of ice. Okay, so this is the plan. Okay, so after you plan this out, the next thing you are going to do is you are going to pretty much after you calculate everything, you're going to add them all together, right? Because we care about the final process, right? What from here to here, right? So that therefore you're just going to add them up. So I'm going to start with ice at negative 10 to I at 0. So in this case, what you are going to do is you're going to plug in, right? So mass of ice, right, times specific heat of ice, and then times to the T, right? So, and remember, this is going to come out to be joule. Okay, so we want it to be in kilojoule. So therefore, final step would be convert that joule to kilojoule. You can do the second step as well. Like after you get this answer, then you can convert to kilojoule. That's fine too. Or you can just put it in one single step. That's fine too. So if you calculate for all of those unit cancel out, you are going to get your answer in kilojoule. Okay, so that is only the first step. Okay, the second step would be using delta H of fusion. So in this case, remember N is mole, right? So therefore, in this case, what you are going to do is you are going to convert grams to mole first using molar mass. And because we already have mole here, the next thing is using the heat of fusion, okay, of the water, right? So in this case, it's 6.02 kilojoule. So if you calculate for this, you are going to get 3.0 kilojoule. Last one, do the same thing, right? So Q equal MCAT, but except using specific heat of water instead of ice. Okay, so if you do this correctly, you are going to get 3.2 kilojoule. One common mistake that student did that I noticed is going to be if they forgot to convert this to kilojoule, let's say it's in joule, and this is also in joule, they start to add all of this up together, you cannot do that because different unit, you cannot add different units. Okay, so that's one common mistake that I noticed. Okay, so make sure that all of these units are the same. Okay, so in this case, because they all are in the same kilojoule unit, you can add them all together. So that means this process, in order to convert 9 grams of ice at -10 degrees Celsius to 85 degrees Celsius of water, it's going to require 6.4 kilojoule. That's what it means. All right, example 2. In this case, I would like you to actually pause this video and then attempt this yourself first, okay, before you actually look at my work. Okay, so pause video now, and when you're ready, you can resume the video again. Now let's check your work together. Okay, so in this case, the plan would be we are going to warm water at 25 degrees Celsius to 100 degrees Celsius, right? And then water at 100 degrees Celsius, this is boiling point, right? It's going to change state. Once it changed state, you will notice that temperature stay constant, right? So temperature of water and steam have to be the same. Okay, so now once it all becomes steam, then when you heat it further, then the steam would increase temperature. Okay, so it would involve with 3 steps here. Okay, so the first one, you are going to use MCAT because it's involved with temperature change, right? And then the second one, you are going to use heat of vaporization. Okay, and then the last one, you're going to use MCAT, but it's the specific heat of steam instead. Okay, and then you are going to add them all together. Okay, so this would be your final answer. Now let's take a look at the type of calculation that will involve with this concept. Okay, so in the example 1, okay, you're pretty much looking at the amount of heat involved with ice at a certain negative degree Celsius, right? And then you are going to heat it to a certain degree Celsius of water, right? So this is example 1, right? And then example 2, you see that it's given water at a certain degree Celsius, and it's asking to convert that to steam, right? To a certain degree Celsius of steam, right? So that would be example 2. On the exam or even the homework, it might ask you differently, right? So it might ask you to find this whole thing, right? The process would be the same. Okay, so the idea of it is going to be the same. This would be example on homework, right? Or might be on exam, right? So you will need to understand each of these steps, right? What does it mean exactly? Or you might also see the reverse process as well, right? So in this case, we are looking at only the endothermic process, right? On the exam or even the homework, you are going to see that it might ask you the opposite, right? So for example, in this case, it might ask you, what is the heat that involved with going from steam at a certain degree, right, to water at a certain degree, right? So it might ask you just that, right? So the process still going to be the same, but except in this case, your answer is going to end up with a negative value because remember, the reverse process would be exothermic, right? So you're going to end up with a negative value of that because the forward is endothermic, so the reverse would be exothermic, so it's going to be a negative value. Okay, or sometimes you are going to be asked to calculate heat that involve with, like going from a certain degree of water and to a certain degree of ice, right? So still the process still going to be the same, right? Except sign of the heat would be negative in this case. So that means you are going to see the type of calculation is going to be within this context right here, right? So going from ice to water to steam, right? And vice versa. And here is a summary of this chapter, right? So we're looking at the heat involved with phase transition, and we're looking at the heat involved with the water process, right? Going from ice to water to steam, right? So we're looking at those and how to calculate the heat involved with each of those processes. Please start working on your homework as soon as possible. And if you have any question, please visit me during office hour.